Hi all, I am Dr. K. Raghuram Mohan Reddy, Associate Professor, Department of Mechanical Engineering, Institute of Aeronautical Engineering, Hyderabad. The course name is Unconventional Machining Process and topic is Abrasive Jet Machining Problems and Solutions. Okay, so here the student can be able to solve the numerical problems on abrasive jet machining. Okay, so at the end of this session, student will be able to solve the problems on material removal rate of abrasive jet machining. Okay, this is the course learning outcome of the today's topic. So not only material removal rate, but also can calculate if the material removal rate data is given, some other parameters like power and the other parameters, okay, which are related to that abrasive jet machining. Okay, right. Right, as usual, non-traditional machining process are broadly classified into mechanical, thermal, and chemical and electrochemical. Okay, so ultrasonic machining over okay, water jet machining, abrasive water jet machining, ion jet machining under mechanical, under thermal, electro discharge machining, electron beam machining, laser beam machining, ion beam machining, plasma beam machining. Under chemical and electrochemical, chemical milling, photochemical milling, electrochemical milling. Okay, so this is the broad structure of the non-traditional machining processes. Okay, so already we have discussed ultrasonic machining. Now we are discussing water jet machining. Okay, so not water jet machining, abrasive jet machining. I think here we have yes, abrasive jet machining. Okay, right. Problem number 1. In an abrasive jet machining, the following data is provided. Okay, air velocity, abrasive particle density, abrasive mass flow rate, nozzle diameter, standoff distance, cutting depth per particle. Okay, now calculate the material removal rate MRR in milligrams per second. Okay, since it is very sensitive, so here we need to find the material removal rate in milligrams per second. Okay, right. Even we can find uh, in terms of minutes also. Okay, not an issue. Right. The material removal rate in abrasive jet machining AJM can be calculated using the following relationship. Abrasive mass flow rate into cutting depth per particle. Okay, what is the formula? Abrasive mass flow rate multiplied with cutting depth per particle. Okay, so abrasive mass flow rate M is 0.05 grams per second. Cutting depth per particle D is 10 power minus 6 centimeters. Abrasive particle density 3.5 gram per cubic centimeter. Okay. Now number of abrasive particles impacting per second can be calculated using this formula. Okay. So abrasive mass flow rate M dot. Okay. M dot. Okay. So here N equal to number of abrasive particles impacting per second is N, that equal to M dot by density, that is abrasive particle density, into velocity of the particle. Okay, right. Where V particle is the volume of the each particle, not velocity, volume of the each particle. Okay, right. Assuming spherical particles. Okay, so here volume of the particle that is in sphere 4 by 3 pi r cube. Okay, right. Without specific particle size, it's challenging to calculate n exactly. So approximate MRR using the available data assumptions. Okay, so with that m dot into d. Okay, so that is pi into 10 power minus m gram per second. Okay, to express in milligrams per second, just multiply with 1000. So 0.5 milligrams per second. So the MRR is approximately 0.5 milligrams per second. Okay, right. Now let us discuss problem number 2. Velocity of the abrasive particles. In an abrasive jet machining, okay, the nozzle is operating with the following conditions. Okay, nozzle pressure, density of the abrasive particles, mass flow rate of a nozzle, diameter. Calculate the velocity of the abrasive particles assuming an ideal nozzle with a discharge coefficient of 0.95. Sorry, 0.9. Okay, right. The velocity v of the abrasive particles can be approximated using the Bernoulli equation for compressible flow through the nozzle. So the formula is v equal to coefficient of discharge into square root of 2p by rho. Okay, where p equal to pressure in pascals. Okay, right. Okay, rho is the density. Okay, CD is the discharge coefficient or coefficient of discharge. Okay, so where CD equal to 0.95 coefficient of discharge, P equal to 3 bar, and rho equal to 4 into 10 cube kg per cubic meter. Okay, right. Now substitute the values. Okay, so V equal to substitute CD. This is 2 times P. This is density. Okay, so that we get at the end 11.635. Okay, 11.635 meters per second. Okay, right. Now problem 3. Effect of standoff distance on kerf width. Okay, so in abrasive jet machining process, the following data is given: nozzle diameter, okay, and standoff distance, that is SOD, 5 mm and 10 mm, and kerf width as and kerf width at SOD 5 mm is 0.8 millimeters. Okay, assuming a linear relationship between SOD and kerf width, calculate the kerf width at standoff distance of 10 millimeters. Okay, right. Solution: if the kerf width WK increases linearly with standoff distance SOD, then WK2 is equal to WK1 into SOD2 by SOD1. Okay, SOD of second one to SOD of first one. Okay, where WK1 equal to 0.8 mm is given. Okay, see here 0.8 mm. Okay, right. SOD1 5 mm, that is given. Okay, this one. This is SOD2. Okay, 10 mm. Okay, substituting the values, we get WK2. Okay, that is increased the kerf width. Okay, so the kerf width at the standoff distance 10 mm is 1.6 mm. Okay, very simple one. Okay, right. Now problem number 4. Energy utilization efficiency. During an abrasive jet machining process, the energy supplied to the air stream is 200 watts, and the actual energy used in material removal is 8 watts. So we have to find the energy utilization efficiency of the abrasive jet machining process. Okay, so here we have used 8 and given is 200. So energy used in material removal to the total energy supplied is the efficiency of the utilization of the energy. Okay, into 100%, so that we get 4%. Okay, therefore the energy utilization efficiency of the AJM process is 4%. So problem number 5. In an abrasive jet machining process, the following parameters are provided. Abrasive flow rate, nozzle diameter is given, jet velocity given, density of abrasive particles given, material removal rate is also given. Calculate the time required to cut a slot of 50 mm length, 1 mm width and 0.5 mm. Solution. Okay, so volume of material that we can calculate as usual, length, width into depth. Okay, so substitute the values. Okay, length given and width given and depth given. Okay, so we got volume of material. Okay, so time taken formula would be volume of material by MRR. Why? Because already we know what is MRR, material removal rate, volume of material removal by time taken for machining. Okay, so we need time. Okay, so that VMR by MRR. Okay, volume of material removed by MRR. So that it will be 125 minutes. Okay, right. Problem number 6. Calculating nozzle wear rate in abrasive jet machining. In an abrasive jet machining process, the following parameters are observed. Nozzle diameter is given, jet velocity is given, operating time is given, wear ratio is given. The nozzle material has a density of 8 grams per cubic centimeters. Calculate the weight loss of the nozzle after 50 hours of operation. Okay, right. Now, weight loss equal to wear ratio into nozzle surface area into operating time into density of nozzle. Okay, and for surface area, pi into nozzle diameter into nozzle thickness. Okay, so these two formulas can be used to solve this problem. Okay, so then volume loss equal to wear ratio into nozzle surface area into operating time, and mass loss is volume of loss into density. Okay, right. So substitute these values so that we will get volume loss and mass loss. Okay, we get volume loss 18 grams per centimeter square. Okay, and mass loss 144 grams per centimeter square. Okay, so the weight loss of the nozzle after 50 hours of operation is 144 grams. Okay, right. So these are the references. Okay, and thank you very much. Okay, so with this, let me conclude.
Like, share and subscribe. Hit the bell icon for more updates.